Hello and welcome to this clip going through organic testing and analysis. It's designed to review the stages of testing an organic compound, starting with a simple lab test that you come across in your A-level chemistry lessons through to combined spectral analysis. So the idea is, by looking at each of the stages in turn and then having a think about them as a part of an ongoing process, when you see more challenging, longer answer unstructured questions in an examination on this topic, you'll be able to think the way a professional chemist thinks, rather than what is this part of the question about, what is that part of the question about. By seeing the whole thing from start to finish, you can then visualize more clearly what possibly you might need to put down. And towards the end of the clip, we'll look at a couple of such questions where one is less structured, so it's longer answer but less information is given, and the other is more applied in its nature with a little bit of calculation thrown in for good measure. So the idea is, behind all of this is they want to see how resilient you are. So they're going to make questions that seem hard at first, but after a little bit of thought, you can hopefully start to see a way in. So the general organic testing process starts with laboratory tests for functional groups. So this confirms that certain functional groups are present. After that, you've got to confirm this. And your spectroscopic analysis follow-up will confirm what the laboratory tests have suggested and then give you further structural information. So you'll get given some of this information in a question. You might not get all of it, but the information that you do get given will allow you to work out the answer. Obviously, the more they give you, the more deduction you're expected to carry out, the more you're expected to do with the information you're given. So lab tests for functional groups generally gives us initial information, which is then followed up and confirmed by spectroscopy afterwards. So if we were to look at the acidified dichromate test, that identifies primary and secondary alcohols, as you can see from the equation. It also positively identifies aldehydes. So whenever you write the equation for this functional group test, you must always write in oxygen as an O, capital O in square brackets, to show the oxidizing agent. It's also written in to balance the equation, so it's actually one of the reactants. So it's not written over the arrow like some people do. If you look at the examples on the screen, you'll see that the K2Cr2O7, that could be written over the arrow, but the oxygen is actually an atom that is used to oxidize the alcohol or the aldehyde. So therefore, the oxygen atom comes from, not the oxidizing agent. It's a shorthand for doing this. So Tollens' test for aldehydes is also an oxidation, by coincidence, so you could write it out the same way. And the positive result this time is a silver mirror forming, as you can see on the left-hand side on the photograph. So next we'll have a look at carboxylic acids, but before we do that, it's worth pointing out that this test doesn't work for ketones. So I'll come back to carbonyls a little bit later. First we'll have a look at the carboxylic acid test. So the carboxylic acid functional group is very easily tested for. You simply put either a solid carbonate or hydrocarbonate, as hydrogen carbonate I should say, or you could put in a solution of carbonate or hydrogen carbonate. The commonest one used is sodium carbonate or sodium hydrogen carbonate. And what you're after is effervescence or fizzing due to carbon dioxide gas being given off. So the 2,4-DNP test gives an orange precipitate in the presence of the aldehyde or ketone functional groups. So this precipitate can then be filtered, purified by recrystallization, and then its melting point checked against melting point data. So here's a little exercise for you. I provided you with some 2,4-dinitrophenyl hydrazone melting point data, and it tells you that an unknown carbonyl reacted with 2,4-DNP to produce a coloured solid hydrazone, and the melting point was found to be 142 degrees C. So you look at the data on the table and try and work out which of the possible candidates in blue it could be. So pause the clip and then play once you think you've worked it out to check if you were right. So 144 degrees C is the closest. So the original carbonyl compound must have been pentan 2-on, or 2-pentanone, as they've said in this table. So I've only gone over some of them in detail in the last few slides, so it's worth just pausing for a sec and making sure that you're aware of all the different functional groups you need to know the tests for. So if you're watching this at home, this might be worth just pausing and copying down this particular table, because it's been specifically done for our specification. And you need to know the type of reaction, the typical equations, the positive observation, the chemical test, of course, and the functional group. It's also useful to have an awareness of the mechanism, because sometimes it will feed into your knowledge of different mechanisms. So before we go on to spectroscopy, let's have a quick look at a past paper style question with a little bit of a twist at the end with some deductive maths thrown in for good measure, because it's the kind of question you might see in an actual paper. So let's see if we can complete this table. It might be worth pausing and giving it a go. If you've got the stuff from the previous slide down or have access to it, it might be worth trying it out. I just thought I'd mention as well that you don't need to know the test for amides. This is a slightly off-specification question sheet. It may be needed for other specifications, but for our current specification, OCR-A, it's not needed at this time. But for reference, it's pretty much the same as the presence of NH4+. So we use aqueous sodium hydroxide, warm it a little bit, and test for the evolution of ammonia gas by using a damp red piece of litmus paper or universal indicator paper. Okay, so let's crack on with this. So the first one's quite straightforward. The bromine is decolorized from orange to colorless. So obviously the next one is your solution of dichromate in the presence of dilute H2SO4. And you can see I've bolded the dilute because it doesn't work with concentrated, it has to be dilute. It's not that it doesn't work with concentrated, it just happens too quickly. We need it to happen in a more controlled manner, so we use dilute H2SO4. So before we go any further, it's worth pointing out that at this stage you need to maybe distill the aldehyde off, because it's a primary alcohol that you're testing for, as you can see. So you need to confirm the actual RCH2OH part of the molecule that you started with. So once you've distilled off the aldehyde, you then add the distilled aldehyde to warm Tollens reagent, and the formation of a silver mirror on the inside of the test tube indicates CHO. For the presence of a carboxylic acid, you obviously add a carbonate or hydrogen carbonate. Sodium is as good as any, sodium hydrogen carbonate or sodium carbonate. And effervescence would indicate the presence of the carboxylic acid functional group. And the one at the bottom is really the oxidation product of the second one down, isn't it? So we've talked about that one already. It's the same idea. So let's move the page down a bit. And this time it's a calculation. So before we do that, let's have a look at the first part though, sorry. It says, explain why in testing organic compounds for halogens it's necessary to boil a compound with NaOH and then acidify with dilute nitric acid. So what happens is the OH minus in the sodium hydroxide, under the influence of heat, doesn't have to be boiled, gentle heat will work as well, will hydrolyze the haloalkane, and it releases Cl minus, and Cl minus goes on to react with AgNO3 to form a precipitate. And the presence of an acid dissolves any unwanted Ag precipitates. If you may remember, silver compounds tend to be insoluble in water. Silver nitrate is a bit of an exception. Most silver compounds tend to be insoluble in water, which is the whole point of the silver nitrate test, because you want a chloride or a bromide or an iodide precipitate. So now they want us to calculate how many moles of chloride ions were released from 1 mole of compound X. So if we go back to our compound, so looking at our data, we've got 1.6 grams of compound X, which is C7H6Cl2. That gives us 161 grams per mole. So that means that we have 0.01 moles of X in 1.61 grams. If we do the same thing with our silver nitrate, we can obviously work out that 1.435 grams is 0.01 moles. So this next bit requires a little bit of deduction. If you look at the number of moles of silver chloride to the number of moles of C7H6Cl2, you'll see it's actually 1 to 1. So that must mean only one chlorine atom on X is capable of removal by hydrolysis in this method. But X has two chlorine atoms, so the one left behind must be bonded directly to an aromatic ring. Looking at the number of carbons, we can deduce this because there's 7 carbons. That means there's enough to put a benzene ring in. So if we make some room by moving the page down slightly, we can put some possible candidates in. So on each of these, it's the aliphatic bonded chlorine, not the one that's bonded directly to the benzene ring, that would be the one that's hydrolyzed. So just to clarify which one I'm talking about the one that's part of the CH2Cl group. Okay, so let's now go on to look at spectroscopic methods of analysis. So the mass spectrum tells you the fragmentation patterns and the MR of your compound. And you mustn't also forget that the difference between peaks may give fragmentation clues, and the base peak with the greatest intensity indicates a likely fragment for your compound. So in this particular example, you can see that the base peak is at MZ equals 57. So that means a 4 carbon fragment such as C4H9 plus would be likely. And I can't stress this enough, it's really important to write in a positive charge next to your fragment in the analysis. If you don't write in a positive charge, you won't get a mark for it. Now if you look at the other ones, you've got C3H7 plus, you've got C2H5 plus. If you were given other information about this particular molecule, as it happens, is an alkane. But if, let's say, it was a carboxylic acid, or it was an aldehyde, or you knew something else about it, you could then start deducing which of those fragments might have oxygen in them, for example. So I mentioned the differences between peaks. If you look at the difference between 29 and 43, or the difference between 43 and 57, it accounts for CH2 really, doesn't it? So you can see the differences between the two possibilities. What's interesting though is the molecular mass is 86. So the example this particular spectrum came from indicated that the molecule was an alkane. So working on the idea that peak at MZ equals 57 and the peak at MZ equals 29 together account for a molecule that would add up to 86 in total, which is your MR, your molecule would have to be 6 carbons long. So for now we're going to have to stick with C6H14. We're not quite sure whether it's branched or not, but further information in the question would be needed before that kind of thing would have to be taken account of. So moving on to infrared spectroscopy, this gives you ideas about what bonds might be present, because it's technically based on the absorption of infrared energy by covalent bonds. So I've given you 2 typical spectra here, and it's also quite interesting to note how you can also tell by the absence of a peak what might or might not be present. And what this allows you to do is to think a little bit deeper as to not just what bonds are present, but also what that might mean in terms of what functional groups are there. So for example, on the top spectrum here, you can clearly see that there's a peak for a carbonyl group, C double bond O. But in the spectrum below, it's not there. So you can clearly see a difference between one functional group and another, the alcohol functional group versus the carboxylic acid functional group. So using NMR spectroscopy allows us to tell what environments are present depending on the type used. So you've obviously got hydrogen, you've got carbon, you've also got phosphorus and fluorine as well, but those two are not on the spec. So carbon-13 spectroscopy tells us the carbon environments that are present. So what this can allow us to do is distinguish between isomers. So if you look at the 2 isomers at the bottom, there's slightly different carbon environments in each one and slightly different numbers of carbon environments in each one. So looking at the isomer on the right, for example, you can see there's a slight difference in the absorption of the peaks, and that's reflected by the structure of that particular isomer. You can see clearly that there's more carbons present in the CH3 environment than are present in the CHOH environment. But the 2 isomers are exactly the same. And you can see that obviously that they're both C3H6O. So let's now have a quick look at NMR hydrogen spectroscopy, or proton NMR as it's called. So when you're doing a proton NMR analysis, it's always advisable to do it as a table rather than lots of different sentences. The reason is twofold. First of all, it allows you to collect your thoughts and ideas easily as the candidate, but secondly, it also allows the marker, the examiner, to see clearly what you're talking about, and you're more likely to get marks for it. So when you're filling in the chemical shift part of your table, you use the spectrum you're given or information in the question. When it comes to writing out the hydrogen environment that each chemical shift represents, try to base that on the type of molecule you're dealing with. For example, the question might tell you that you're dealing with an ester, or it might tell you that your mystery molecule has given a positive test with 2,4-DNP, for example, so you know it's a carbonyl compound, so you can think aldehyde or ketone. When you're talking about splitting, you must use the n+1 rule clearly. When you're doing the adjacent hydrogens, you always need to watch out for more than one adjacent environment, which would suggest a multiplet. Another thing to watch out for is if the adjacent environment is identical to the one you've just looked at, then there's no splitting taking place, or it won't be recognised. And finally, the integration trace might not always be given. Some questions use it, other questions don't. So if it's not there, don't feel you have to suddenly put it into your table and try and guess. So let's now assume that we knew a little bit more about this molecule, and we were told that it was C3H6O2. So we know what the integration traces are, so we can start putting in the chemical shifts. Now, even though we don't know anything else about the molecule, the fact there's two oxygen atoms suggests either an ester or carboxylic acid. In addition, there's two proton environments, so if you've got 6 in total, some must be equivalent. And we used the fact that there were two peaks, peaks A and B, to work out that there were two proton environments. We can also tell that the areas under the peaks are roughly the same, so this indicates an equal number of protons in each environment. So looking at the analysis of the first peak at 2.2, I've tried to be specific, haven't I, when I've talked about the hydrogen environment. It's a singlet, which means there's no adjacent hydrogens, and its integration trace is 1. So I've now done the same for the chemical shift at 3.7. Now you'll notice that the actual question itself gives me the integration trace. So they're unlikely to give me marks for simply writing down or copying down 1 and 1. So I need to think about this. We have 6 protons in a ratio of 1 to 1. So all we now know is that they're a 1 to 1 ratio. So we can actually adjust both our stated environments column and the integration trace column. So now we're ready to try and work out what our structure is. So finally, there's no singlet present at the chemical shift at 12.0 ppm. So it can't have an OH environment, so it leaves us with only one option, that's an ester. So that's CH3COO-CH3. So combined spectral analysis pulls all the ideas together. So let's try a little problem on you now. I'm going to give you this information, this spectra here, and I'm going to tell you a little bit more about the molecule, and I'm going to leave you for a few minutes to try and work out what it might be. So let's make this a levelled question, in fact, of the more modern style from the OCR specification. So let's make it a 6 marker. They give you all this information, and you have all this space now to put something down. So the first thing I'd do is I'd lay it out in 3 stages, so I could say something about each of these. Now, it's important to point out here, I've imported these images, and they came with a little bit of analysis already. So you wouldn't, for example, get anything like the empirical formula has mass 44, therefore molecular formula is C4H6O2. So therefore you'd have to work some of that out yourself. But we can try and sort of make it into a level style question and get something out of it that way anyway. So if we do the infrared and mass spectroscopy first, and then try and pull it together using the hydrogen NMR at the end, we can see that there's a peak at 2,500 to 3,300, and also one at 1,700. Now what I'm trying to do in all cases is to actually match the values that I'm quoting to the actual data sheet I'm given. So 1,700 falls within the value of the data sheet. The data sheet, I'm just reading it off here, says 1630 to 1820, but it's quite clear that that peak matches 1,700 if you look at the scale. The OH peak is not quite so clear, so what you have to do there is actually quote the range. So the range from the data sheet, I'm reading it off again here, is 3,200 to 3,600 centimetres to the minus 1. So now looking at my mass spectroscopy analysis, the M plus peak at MZ equals 88 means the MR is 88 grams per mole to the minus 1. The base peak at MZ equals 43 suggests a CH3C double bond O plus fragment. Interestingly, there's no major fragment at MZ equals 45. So that would suggest there's no COOH plus. So that in itself would suggest that it's not a carboxylic acid. So I've done a little table in the same way that we talked about earlier. So we can take each of the individual peaks. I'll start from the one at around 2.2 or 2.1. So because we already know we have a CH3C double bond O, or at least the peak in the mass spectrum suggests so, I'm just drawing your attention to now. Obviously you wouldn't have been given that little bit of a hint in an actual level question, but it's worth now saying that in our proton environment it's CH3, which is a little bit more than the data sheet suggests. So, like I said earlier, the data sheet is a bit generic. If you can give information that makes it a bit more specific, then always a good idea. So I've laid out my table, so I've taken each of the peaks in turn. Now the only thing left to do before I try and pull a structure together is work out what the actual molecular formula is, because I forgot to do that. So you can see that I've worked out in the mass spectroscopy analysis part, the M plus peak is 88. So I've slightly adjusted my mass spectroscopy analysis. Obviously in a question I would have put that in earlier, so it's my slight mistake not to mention it earlier on in the analysis, so apologies for that. So now we can try and propose a structure. I've left a little bit of space down at the bottom of the screen. So something like a hydroxy ketone, such as CH3CO, CH2, CH2OH, would match all of these criteria. So, in fairness, probably all of that work would not be 6 marks, if I'm totally honest with you, but I thought I might take the opportunity to show you how you could lay it out in a nice and easy way, so that you could pick up the marks bit by bit as you go through. So the key message really is to try and structure your answer nice and cleanly into different sections like I've done here. It makes it easier on you, it also makes it easier on the examiner. So this is an example of a more unstructured, applied style of question. There's a lot of information in there, and there's quite a lot of room in which to put stuff down. So if we just bring the page down for a minute, you can see it's an 11-mark question and they want a mechanism. So there's quite a lot they're actually asking of you here. So let's just read through it together. It says a hydrocarbon A, C8H8, reacts with hydrogen bromide to form compound B, C8H9Br. So what I'll do is I'll highlight different parts of it and then possibly put down what that says to me on the right hand side as little notes to myself. When you've got a question like this, there's nothing wrong with actually writing some stuff down the side. Now clearly it says don't write in the margin, so in an exam you mustn't do that, but you could put it down on the left hand side, couldn't you? Over here somewhere, for example. So let's pull the whole thing over there So now we've got some space to play with. So in the first sentence, they essentially tell us that, don't they? So don't be shy to put something down like suggests an addition reaction alkene equals A. So compound A might be an alkene. After all, we also know it's a hydrocarbon. So alkaline hydrolysis of B, which is C8H9Br, gives a compound C8H10O, which is converted into compound D on treatment with an acidified solution of potassium dichromate. So the fact that we have acidified potassium dichromate must mean that we have an oxidation going on. So C8H10O must be a primary or secondary alcohol. So we've got several possible things we could choose here. We've got to use other information that we've got. So now it's time to actually start breaking up our answer into what the infrared tells us, what the mass spec tells us. So the information they give us about the mass spectral analysis is that the base peak of compound D has an M over Z of 105, which would be the equivalent of its mass. However, the MR of compound D, which we're told is C8H80, is 120 grams per mole to the -1. So the fragment that's broken off has an MZ value of 15, therefore most likely to be CH3+. Now, as I was thinking there, I also realised I didn't fully explain what my deductions had been for the hydrolysis. So I worked out that CH10O must be primary or secondary alcohol, because haloalkanes, which is obviously compound B, are hydrolyzed alcohols in the presence of OH-. So we can't really say anything more about the mass spectral analysis. We can go on to the infrared information now. So I'm just going to bring the page down a bit so we can focus on the information that's right at the top now. So we can write out the absorptions for each of the compounds that were given, compound A, compound C, and compound D. So we still haven't quite sorted out where the 105 comes from for the base peak. So I'm going to bring the page down a little bit to try and explain that. So we know that A is an alkene, and we know that what happens is the alkene reacts with HBr to produce a halogenate alkane. So notice we don't actually know what any of the other atoms are yet. We just know that these particular changes are taking place. So looking at the number of carbons I've actually got to play with, I've got to use quite a few up, don't I? So to make it up to 105, I'm proposing that we have a benzene ring with a carbon with a double bond and an oxygen coming off it for compound D. So that must mean that all the other compounds must also have a benzene ring. So our 4 compounds are these here. So what they did also ask us to do is a mechanism, and it was the mechanism for the conversion of compound A into compound B. So moving it down a bit, I can just pop that in at the bottom left-hand corner. So just at this second stage here, it's worth pointing out this is the more stable carbocation, according to Markovnikov's rule. So obviously the final product that we get, the most likely product, is compound B. Okay, so hopefully you found this fairly useful as a way to pull together some of the ideas that you've come across at different points on the course. I think possibly the key bit of advice would be to try and make sure that you always sort of break up your answer into sections so that you make it easier on yourself to write it down, and also easier on the marker to give those method marks to you. So thanks again for listening, and bye for now.